Tell you what, let's do the rest of this later, okay? Is this the...
She's part.
Ah, okay.
So that's homework.
This is last homework. Okay.
Yep. I was brilliant, and I marked mine with this. Can I grab this?
Okay. That was good. Yeah. I'm going to use that.
Yeah, there's another one in there somewhere, but it'll be easy to find.
All right. I'm just going to take this away so people will go sit down. Okay. We have plenty to cover today, so let's get started. Let's see. So we really have two half lectures today. The first is finishing up the material on computational learning theory. As you remember, we left you with this cliffhanger question, but what if the hypothesis space is infinite? And then the second half, we're going to just take a giant step backward and kind of look at what we've covered during the first half of the semester, partly in preparation for the midterm. Okay, so let's start right in. So last time, really, the key result that we proved as a class was this one, that in this PAC learning setting that we talked about, where examples are created by first drawing an X at random from P of X, some underlying distribution like students coming in the door. And then once we have an X drawn from that random distribution, we'll have a trainer label that X in a deterministic fashion and without ever making a mistake. So the randomness here in the training set comes from P of X, not from the teacher making labeling mistakes. And in that setting, we found that we could prove, and we did, in fact, that the probability that the version space is not epsilon exhausted, or put in another way, the probability that we have a hypothesis that has survived all the training examples without making any mistakes after M training examples, and still has a true error that's at least as bad as epsilon, then that probability is bounded. And we proved what the bound was. So, in other words, the probability that there exists a hypothesis that will have zero training error on these M randomly drawn examples and still have a true error that's worse than epsilon is at most this quantity. And then we showed that we could use that fact, just re-express that fact really, to answer questions like, well, how many training examples M will suffice to guarantee us that probability of making a mistake is, or the probability of having a worse than epsilon hypothesis still in the running is at worst delta. And we came up with that expression. Or we could flip it around and equivalently calculate, well, how many examples do we need to look at to bound the true error? Essentially using epsilon as our indicator of the bound on that. Okay, so that's what we talked about last time. And one thing that I glossed over, but I just want for completeness to tell you the definition of PAC learning. Because if you read papers in this area, you'll see people talk about they've proved something about a PAC learner. And I just want to, for completeness, say precisely what that means. Here's the definition. So let's consider that this definition involves considering some class C of concepts, that is, functions with 1 or 0 as the y value, that the teacher could conceivably want to teach. That's the class C. And it's defined over some set of instances, x. that can be coded with length n. Like these are n Boolean features uniformly distributed, then maybe n would be that. And we have some learner, we'll call it L, that uses hypothesis space H. Then we say that class of concepts is PAC learnable if, but it's PAC learnable by learner L using its hypothesis space H if, for any concept in that class that the teacher might want to teach us, and for any distribution P of x, we're using script D here for our P of x, recall, for any distribution that exists over x, and any reasonable epsilon and delta, the learner will, with probability at least 1 minus delta, output a hypothesis with error smaller than epsilon. And we'll do that in time that's polynomial in this. So this is the official definition of PAC learnability. And notice it's couched in terms that are really computational complexity kind of terms, you know, in time that is polynomial. But of course, in machine learning, what we really care about usually, well, we care about time. We care about computer time, but I care more about not the computational complexity, but what we'll call the sample complexity. How many training examples do you have to give, as opposed to how much CPU time is it going to cost? But this definition is in terms of CPU time. And they're actually very closely related, because if you think about it, if you have to prove that this learner can do this in time that's polynomial in how tight our bound on epsilon and delta are, and n, the size of the examples. And also, this is something about the size, the complexity of the class C.
So what is n exactly?
N is the coding length of x.
So one sample of x or all x?
Yes, the code you would use to encode a randomly drawn example of x.
I mean one example or all examples?
It's the length of the code you need to code an arbitrarily drawn example of x.
So just one example?
Yes, but if you to code an arbitrarily drawn example of x, it's influenced, the code you'll need is influenced by the number of examples in
I mean,
x.
so why isn't the conclusion in polynomial in the sample size?
Well, it's not. This is just the way it's defined. So that's why I'm putting it up there. But now let's look at how that's related to sample size. So one way you can prove that your learner will be able to do this in polynomial time is if you happen to have a learner, like all of the ones we've discussed in class, that requires only a polynomial number of training examples and can process each of those training examples in polynomial time. Okay, so even though the definition is phrased this way, almost all of the proofs that something is a PAC learner really prove that the learner can achieve this sample complexity that it can learn to an arbitrary epsilon and an arbitrary delta in a polynomial number of training examples. And then point out that this algorithm also uses polynomial time per example. Okay? And just to kind of relate this back to what we saw here, so here we have our bound on number of examples that will suffice to get us to an arbitrary epsilon and delta. And last time we looked at a few examples, like remember we looked at depth 2 decision trees, for example. And we asked, well, how big is H for depth 2 decision trees if those trees are defined over n Boolean features? And we saw that, I don't know, it was n choose 2 times something was our size of H. And so we actually showed, in the case of depth 2 decision trees, what the sample complexity was. I don't recall what the exact expression was that we came up with. But so the usual way of proving that something is PAC learnable is to actually use an expression, this one or one like it, that we're going to, an extension of it that we're going to talk about today, to find out the sample complexity as a function of, well, we can see what it is as a function of 1 over epsilon. It's clearly linear number bound in that. It's a log bound in 1 over delta, so that satisfies the other part of things. And whether it's linear in n depends on how n is related to the size of h. And for example, that's what we looked at last time for depth 2 decision trees. So the usual way of proving this is to use this kind of expression to calculate what is the sample complexity, that is, how does the number of training examples that suffice, m, how does that grow with 1 over epsilon, 1 over delta, and n, the variable that controls the size of the instances. And then notice that our learner can also do this in polynomial time per training example. Okay. So it's a bit of a technicality, but I didn't want to go through a course, a PhD level course on machine learning, without stating the definition of PAC learning that's the precise one used in the literature. And so you see this is the way it's defined, and that little nice fact over in the blue makes it easy to prove that something is PAC learnable just by showing that it can process training examples in polynomial, each one in polynomial time, and then it needs a polynomial number of examples. Okay, so that was for completeness, because I couldn't rest well at night unless we did this. It probably doesn't change the core understanding that you have about how the number of training examples m depends on things like h and epsilon and delta. But it lets us relate that core understanding to the way people talk about it in the literature. Okay, so now let's improve our core understanding. Here's the cliffhanger question that we left on the table last time. We have this expression telling us how many examples do suffice to learn with our probability 1 minus delta, something with true error at worst epsilon, given that we have a finite hypothesis space. And I left you with this question about what if it's infinite? And the answer is, well, is interesting. Here's the answer. Instead of counting the number of hypotheses in H, a good alternative is to instead find the largest subset of X. Remember, X is the space of all possible instances. We just need to know what's the biggest subset of X where H, our hypotheses that we're considering, can guarantee zero training error. That's actually the property that we need. So it's interesting. It doesn't really matter how many hypotheses are in H. What really matters is how well H can chop up how many different functions H can represent over X, and in particular, this property. How well can it chop up for how big a subset of X can it completely slice and dice the examples? That's really what it means. So let's see, why might that, and oh, this is called the VC dimension of H. This, actually, the size of that subset is called the VC dimension of H. Okay, so let's think about that for a sec. Well, let me do it this way. So before we, and we're not going to prove the theorem for this because it's more intricate, but here's remember one of our big pictures that we talked about was this big picture where we have the Venn diagram of all possible instances and all possible H's. And one thing that we agreed on, and we agreed on it back when we first saw that big picture and then we reviewed it last time. But we agreed that, well, if our hypothesis space is something like, if our hypothesis space is able to represent every possible function definable over X, then we're going to need to see every example in X before we can before we can identify which of these hypotheses it is. Remember we said that. And that's actually the hint. That what mattered there was that we're going to need to see all these examples labeled if H is such a rich hypothesis representation that every possible labeling of the examples can be expressed by some H. But what the VC dimension measures is in the case where that's not, well, even if it is true, the VC dimension then is the VC dimension of H, if H can represent every possible function over these examples, that means H can guarantee zero training error over these examples no matter how the trainer labels them. And then the VC dimension of H in that case will be just the number of instances in X. And if, by the way, that's an infinite number of instances, then we say the VC dimension of H is infinite. But if we have a more restricted, less expressive H that maybe can only guarantee zero training error on these three examples because it has 8 hypotheses that can express every possible labeling of those. Right, if we have 3 examples and we can guarantee zero training error, what that really means is no matter how the teacher decides to label those plus and minus, we've got a hypothesis over here that can do the job. We can guarantee zero training error. We can guarantee a consistent learning, zero training error learning of that. And so if the biggest subset of X for which we can guarantee zero training errors, say a set of size 3, then the VC dimension of H is 3. And so the intuition you kind of see, right? If H is more expressive, if it's so expressive that it can represent any function over X, that means anything the teacher tries to learn or to teach, anything the teacher tries to teach, we can guarantee zero training error. We can learn it perfectly. And that's going to be a very rich, expressive H. But if it's just some smaller finite set, then H is in some sense less expressive. It's less complex. It's actually more biased. There are going to be some functions that might in principle be teachable that won't be learnable with zero training error. We'll still be able to, in the agnostic bounds we talked about, we'll still be able to get some bounds on them. But the essence of those bounds comes from our characterization of the complexity of H this way. Okay, so let's see a little bit more. So the definition I just gave is not one that you'll see often in the literature, but it's identical to the definition that you will see. So let's see. Let's just define a few things and in the kind of more standard terminology. So we say a dichotomy of some set of instances, S, is a partition of S into disjoint subsets. Just the labeling of S is positive or negative. And then we'll say a set of instances is shattered. This is a term you'll see in the literature. A set of instances is shattered by hypothesis space H, if and only if for every dichotomy, every positive negative labeling of those instances in S, there is some hypothesis consistent with that dichotomy. Okay, so again, this would be like having our hypothesis space over here. And if I take these 3 black dots, I'll say those are shattered by H if I have 8 different hypotheses here that can represent each of those possible labelings. When I say labeling, I just mean I'm using the notation here that the stuff inside the circle, this hypothesis labels positive, and the stuff outside the circle, it labels negative. Okay, so if I do it that way, then you can see there are 8 possible. If I have these 3 instances and they can be shattered, then I'll need 8 different hypotheses that can represent each of those 8 circles I've drawn here. And if I do, then I can, like this circle here will represent the case where the teacher labels this positive and those 2 negative. But if instead the teacher labels these 2 positive and that 3rd one negative, then this circle will do it. Then this hypothesis will do it. Okay. Yes?
So if there's a nonlinear function, does this still go in the same way?
Right. So the question is, what if our hypotheses are nonlinear? This actually just doesn't care. This is completely abstracted away from what's the form of H. It just talks about the capacity of all of the H's that we consider to guarantee 0 training error over a set of instances. And so it's really a very general, abstract notion, not tied to any particular hypothesis representation. So that's why these results are so fundamental. They're not about naive Bayes or about logistic regression. They're about all of them.
Restricted to binary classification.
The way we've talked about it's restricted to binary classification. Somebody mentioned after class last time, in the proof that we did, there's nothing that said it had to be binary. It could be any discrete valued y, and the proof that we did in class would still carry through. And I agree with that. But it is a classification problem, not a regression problem. That is, we are assuming it's a function from x to y, where y is at least discrete valued. There are other results for regression, but we're not going to cover those in this class. Okay, so let's go ahead. So then we just say the VC dimension, the Vapnik-Chervonenkis dimension, a wonderful name, named after the 2 gentlemen who invented this, for some hypothesis space H with respect to some instance space X is just the size of the largest finite subset of X shattered by H. It's just another way of saying it's the size of the largest set of instances in X for which H can guarantee 0 training error. Okay. All right. So now let's look at the result. If we use this measure of complexity instead of simply using the count of the number of hypotheses in H, then it's possible to derive a result like this one shown here that's very similar in form to the one that we derived in class, shown on the bottom. And as you see, the main difference is instead of using the log of the size of H, we now use the VC dimension, the Vapnik-Chervonenkis dimension of H. We still have a log of 1 over delta kind of dependence in this. And we have a little bit of a difference here. So we also have a log of 1 over epsilon dependence multiplying our VC dimension. So that's a little different. But essentially this term plays a role similar to this term. And so, indeed, the VC dimension of H is used here as a characterization for the complexity. So this is great, because what this means is now we can handle, you know, when we did our proof in class, we really had two restrictions. One was finite H. Now we can handle infinite H. The other main restriction when we proved it in class was we assumed that the learner could achieve zero training error. And then subsequently, last class, we mentioned that even if the learner could not achieve zero training error, we still could generalize that to the agnostic learning case that we mentioned in class, where instead we just ask that the learner output the hypothesis that makes the fewest training errors. And then we could bound, with a similar kind of expression, the difference between the training error of the hypothesis it output and the true error of that hypothesis. So between those two things, the extending to agnostic learning so that we can cover cases where the correct hypothesis, the correct concept is not even representable in the hypothesis space, and this one where we cover infinite hypothesis space, now we've kind of got a pretty reasonable generic framework. All right, so just to make sure we understand how to translate this very abstract notion of VC dimension into concrete terms, let's look at a couple very simple learners. So suppose that let's start with learner which uses hypothesis space H1. So all the hypotheses in H1 are of this form. First of all, sorry, I should say, X is itself just, well, I have a notation problem here. Let's just say X is a real number. So X is just a point on this number line over here. And then I'll define hypotheses space H1 as the set of all hypotheses of this form. Namely, I'll pick some parameter A, that's the thing that's going to vary from hypothesis to hypothesis. And I'll say my hypothesis is if X is greater than A, then Y is 1. Otherwise, it's 0. This is very simple hypothesis space. Just puts a threshold on X. So what's the VC dimension of H1? 1? I hear a 1. Okay, well, let's see. How would we get this? We would, well, let's consider this instance here. And let's suppose A is this value. Then it's going to label everything on this side of A 1 and everything on the other side 0. And so, what are we doing here? The question we always ask when we want to know the VC dimension of something is, what's the size of the largest set of examples for which we can guarantee 0 training error? That is, we can shatter. That is, we could represent the hypothesis no matter how the permuted labels for that set of instances are assigned. So let's ask, is there a set of one example that can be shattered? And let's consider this example right here. I'd say yes, that can be shattered because I could use A and label it 1, or I could use A prime and label it 0. Right? So so there are two hypotheses here. I just pick a different threshold A, and one of those hypotheses labels this dot a 1, and the other one labels it a 0. So no matter which one of those two things the teacher tries to teach me, I'll be able to do it. Okay, is there a set of 2 points that can be shattered, that I can guarantee 0 training error? What about these two shown here? Well, no. Because if the teacher says 0, 1, I'm toast. Right? Because I've got to put my threshold over here if I want to label this thing with 1, and then it's going to label both of them a 1. Right? So I can't really, with this simple hypothesis language, shatter those 2 points. You see the problem? Okay. And so that's it. So the VC dimension of this thing really is 1. There's just 1 point for even these 2 points. I can't guarantee 0 training error. There's a way to assign the labels so that I can't represent it. Okay, what about H2? What's the VC dimension of that? Notice now I allow y equals 0. I allow both ways of then else to assign the y's. So now clearly this is more expressive, so I can surely shatter 1 point. Can I now shatter 2? Yeah, right. Can I shatter 3? No, why not? 1, 0, 1. If I line up the 3 points in a line and the teacher labels them 1, 0, 1, and I need closed intervals to do that. I've still got open intervals. Okay, VC dimension is 2. What about this one? Closed intervals. But it's a very particular kind of closed interval. So again, now for the hypotheses vary by choosing an A and a B, but now I have this particular form of then else. So can I shatter 2 points? Yeah, that's pretty easy, right? I can make the interval include them both, include them neither, include either one. That'll be fine. What about 3? Can I shatter 3? No. I still have the 1, 0, 1 problem, right? So there's a labeling of those 3 points that cannot be represented by this, right? Because I basically have to define an interval where the things in the middle of the interval are 1, the things outside the interval are 0. Can't do that here. Okay, so this has a VC dimension of 2, even though, well, I won't say even though. It just has a VC dimension of 2, just like that other hypothesis language, which is different from it. Okay, and what about H4? 3. Can I do, okay, so here we can represent this labeling with H4 because now I'm defining a closed interval where inside the interval it's 0 and outside the interval it's 1, so I'll be able to do that. Similarly, if the teacher gives me this one, I'll be able to handle that too because I'll just use this form. And if well, I guess there are 8 of these all together, but you can convince yourself that we could do all 8 of those possible labelings of these 3 points. And therefore, we can guarantee 0 training error no matter what the teacher tries to teach us about these 3 points.
The VC dimension can just be arbitrarily large.
The VC dimension can be arbitrarily large. It can be infinite. Okay. So it's a pretty simple idea. Let's look at a more interesting example. Lines on a plane. So here's a hypothesis language where now my x is real numbers, 2 real numbers, points on a plane, and my hypotheses are decision surfaces on that plane. That if the points lie on one side, they can label that 1. And notice with this representation, if I just flip around the weights, the signs of my weights, I can put the 1 on either side of the line. So what's the VC dimension of lines in a plane? Can I shatter 1 point? Obviously, yes. Can I shatter 2 points? Yes. Can I shatter these 3 points? Okay, so to prove that you can shatter these 3 points, you have to tell me that for any of the 8 labelings that I might assign, you've got a hypothesis that'll handle it. Okay, I agree with you. Can you shatter 4 points? No, you can't. I agree. So the VC dimension, oh, what about these 3? Can you shatter these 3 points? Right, I agree with you, because I can do the 0, 1, 0 hassle to you. Okay, so we have 3 points we cannot shatter. We have a different set of 3 points we can shatter. What's the VC dimension? 3. The VC dimension is the size of the largest shatterable subset of instances. The VC dimension is the size of the largest subset of instances for which you can guarantee 0 training error. And we can guarantee it for this subset, and it's of size 3. VC dimension is 3. So we don't have to be able to shatter every set of size 3. There just has to exist some set of size 3 that we can shatter. And if there existed a set of size 4 we could shatter, that would do it too.
So actually we have to prove that we can't shatter any set of size 4.
Yeah, and this is the painful thing. So we haven't really proved that the VC dimension is 3, have we? What we've done is we've proved that it's at least 3. To prove that it's 3, we have to somehow prove that it's impossible to shatter every single subset of 4 points, which I leave as an exercise for the listener. But it really is 3. In fact, so this is kind of interesting, right? Because now we're getting to algorithms we know and love. Like, what has a linear decision surface among the algorithms we've talked about? Logistic regression, right. So what this is telling us is if we have a logistic regression classifier trained over points where our training examples, where our examples have 2 features, x1 and x2, which are real values, points in a plane, then the VC dimension of logistic regression in that case is 3. And going back to that expression we just looked at, we could plug that into our formula to ask how many training examples will suffice to guarantee that with probability 1 minus delta, we're going to get a hypothesis whose true error is at worst epsilon. So it really applies. Now, what if we had a logistic regression in higher dimensional space? Instead of points on a plane, what if it was points in 3 dimensions? What if it was points in 17 dimensions? So there's a nice result, which we won't prove, but you could consider this on your own. The VC dimension of linear separating planes in n dimensions is n plus 1 in general. Okay, and that's what we just saw for 2-dimensional points. We agreed the VC dimension of lines in a plane was 3. In a 17-dimensional space, hyperplanes have a VC dimension of 18. Interesting. So this tells us something about the sample complexity for logistic regression. By sample complexity, of course, what I mean is how the demands for greater volume of data, how does the number of training examples, M, that we need, grow as we add more and more variables to our logistic regression classifier? Well, the VC dimension grows linearly in the number of variables in X, the number of features in the X vector. And what did we say Let's go back there and look. So if we go from, if we double the number of features, well, if we double the number of features in our examples from 10 to 20, the VC dimension is going to double also, right? It'll go from 11 to 21, approximately double. And that means the number of training examples we're going to need to get the same delta epsilon bounds is also going to double, except for this annoying log of 1 over epsilon term. But roughly speaking, is going to double. Interesting, right? So now this tells us something about how the need for training data is influenced by how many variables we're looking at. And this says, well, just linearly. It's not that bad. In the case of planar decision planes in n-dimensional space, like logistic regression. So this stuff is actually kind of interesting that way. The particular bounds are maybe not all that tight, but the complexity results are interesting. The fact that you really will need about twice as many training examples if you double the number of variables in your logistic regression. So that's actually kind of interesting. Okay. So just to make sure you understand VC dimension, here's a simple quick quiz question. The answer is yes. So what's the explanation for why the answer? So the question is, for any finite hypothesis space, of course finite hypothesis spaces also have a VC dimension. Can you give an upper bound on the VC dimension of any finite hypothesis space? Well, let's see. What does that mean? Remember that for us to get for us to say the VC, let's just say the VC dimension, we have some hypothesis space H, and let's say its VC dimension is K, just so we have something to talk about. Okay, so what does this mean? This means that there exists some set of K instances in X for which we can guarantee zero training error. Again, assuming that y is a Boolean variable, that the function assigns ones and zeros labels to the data. What does that say about the number of hypotheses that we need? If we can shatter a set of K instances, remember when K was, for example, 3 in the simple points in the plane example we looked at, how many different labelings of those 3 points did we need? 8. Right. So if the VC dimension is K, that means there's a set of K points that can be shattered. That means how many different labelings can be expressed? 2 to the K. So H can express at least 2 to the K functions. So that means that H has at least 2 to the K different hypotheses in it. Right? Good. So now the size of H is related to the VC dimension K. And that's basically all we need. So now K and log base 2 of H, that's it. Right? So it's just a simple idea. But of course, you can't shatter K instances unless you can represent at least 2 to the K functions. And so H must be at least as big as 2 to the K. Or put another way, if you know the, I should have put my little size of H brackets around there. If you know the number of hypotheses in H, then log base 2 of that is the most points you could ever shatter. Right? remember when we had, let's go back to our big picture just to wrap this up. So in our big picture when we had, remember we considered the case with decision trees. Defined over discrete valued Boolean variables. So he said x is x1 through xn, and these are all Boolean. And then we said, remember we talked about, well, can decision trees express every function, every Boolean valued function over Boolean variables? And we said yes, because we can just, if we have n Boolean variables, we just grow the complete tree to depth n, and we label the leaves as all of the ways we want. So we said, oh yeah, that's because x will be 2 to the n, we'll have 2 to the n instances in it. And then h, of course, will then be 2 to the 2 to the n. All of the possible, the power set of x. All the possible labelings. So h, in that case, would be that. Okay. So in that case, there really were a discrete number of H really is a finite hypothesis space, and it's very big. And so log base 2 of this would be the greatest that its VC dimension could be. But log base 2 of that is still 2 to the n, which is all of the functions you can define over the. Which is the entire set of instances for which we can guarantee zero training error. So this is just a way of showing that what we're saying now is compatible with the claim we made before, that you can't get something for nothing. In this case, the VC dimension is just the entire set of the size of the entire set of examples. Okay. All right, so there are plenty of examples here that you could think about more at your leisure. I'm not going to go through them now. The one thing I do want to say is, and then we'll leave VC dimension. By the way, somebody asked me, is this going to be on the midterm? Yes, but you're not going to have to prove deep theorems about it. So you should be aware of the ideas, the core ideas we're talking about, but you shouldn't stay up all night worrying about how you would prove that expression that we gave about how m is related to the VC dimension. We're not going to ask that kind of question. But you should be aware of the basic results. But here's one other kind of interesting result that I just wanted to make sure you knew about. It's a very reasonable question. So these bounds that we've got are, I've pointed out several times, that in practice they don't really tell you exactly how many training examples you need. They're usually kind of conservative. If you give as many examples as these expressions ask for, you usually have more data than you need. People have done experiments to see how close this is to the empirically observed probability of outputting a hypothesis with epsilon error, and what they found is that the bounds are kind of loose. They exaggerate the number of training examples you really need. But somebody developed an interesting result that gives us some insight into whether we might in the future hope for a tighter bound. And while we can keep hoping, it doesn't look that likely in terms of at least the order of the bounds. Because up here in the expression that we have, we see that the number of examples we need varies with the log of 1 over delta, and the VC dimension, and the log of 1 over epsilon. But here's another interesting result, which, unlike what we talked about, actually, let me preface this way. The result that we've talked about is, in a sense, a worst case bound. It says regardless of what P of X is, and regardless of what concept the teacher is trying to teach, if we get M examples, that'll do it. That'll suffice. So that bound has to cover the worst possible P of X and the worst possible concept that the teacher is trying to teach. So here's a different bound from the other end that says consider any class of concepts with some VC dimension more than 1, and any learner and any reasonable epsilon and delta. Then there exists some distribution D, some P of X, and some target concept C that the teacher could choose to teach, such that if the learner L observes fewer than this number of examples, then there's some probability, at least delta, that they're going to output a hypothesis with worse than epsilon error. So in other words, with high probability, they're going to fail the delta epsilon test. And this result says, here's how many examples that if L observes fewer than this number of examples, then it's just, with high probability, it's going to be bad. And what's interesting is not exactly the same as that expression we have there, but we still have this 1 over epsilon log 1 over delta dependence, which is like the first term up there. And now we have something which is VC dimension over epsilon instead of the VC dimension times the log of 1 over epsilon. So there's a little bit of wiggle room here. Maybe that second term can be cleaned up a little bit, but it's not a huge amount of wiggle room in terms of the overall complexity. So this does look like it's probably about as good as we're going to be able to get. And in a way, that's kind of nice, because that means those things we were saying about logistic regression and what if you double the number of features, they're probably going to end up being true in whatever the final bound is that we get. Maybe one of you will get it as part of your PhD thesis. All right. So there's an agnostic version of this as well. And I'm just going to move to the end because I want to get into the second half of, I want to get into a little bit of midterm review. So here's kind of the story, the what you should know part for this. So you should understand what this problem setting is, right? We're talking about classifying examples where the training data is generated according to this PAC model. And you should understand that if we have a finite hypothesis space, we have that expression we can use. And you should understand the two restrictions in the proof that we did. We assumed consistent learner and a finite H. And then we can avoid those. We talked about results in agnostic learning if the target function is not in H, and we can't guarantee zero training error. And we also talked about extending to the VC dimension. So the important thing, though, the reason I like covering this is not so much for the quantitative formulas that are here, but for the insights that it gives. So basically, these are very general constraints that any inductive learner in this problem setting, including you and I as inductive learners, will suffer. It's not reasonable to expect that we're going to be able to learn functions with fewer than some amount of training data. And these results give us some insight into that. And the proof that we did in class gives us some insight into why that's the case. And some of these complexity things like, oh, doubling the number of variables in your logistic function doubles its VC dimension approximately. Doubling from 10 to 20 goes from VC dimension of 11 to 21. Those kind of results are interesting, too, because they give some insight into real nature of the statistical problem that we're solving as learners when we do this. So in that sense, it also is a kind of, I think of it as a quantitative characterization of the overfitting problem, right? Because the thing about the bound between how different can the true error be from the training error? Well, that's exactly what we mean by overfitting. How bad could the true error be if the training error is so good? Well, that's what we mean by overfitting. It means that we found a hypothesis with small training error, but the true error is really terrible. And what these VC dimension bounds are telling us is just how bad that can be. So actually, let me go back and look at this one picture, because this is as good a midterm review as any picture could be. I don't know if you remember this picture. It was from lecture 1 or 2 in the class. But this is the picture we showed when we introduced the idea of overfitting for decision trees. And the horizontal axis here is the number of nodes we allow in the decision tree as we grow it. And this is the accuracy that we observe on the training data and on a separate test set of data. And we didn't say it this way when we first introduced it, but now we can. We could say, you could think of this axis as effectively the VC dimension. I'd have to put different numbers on this. But, you know, decision trees with 20 nodes have some VC dimension. I don't know what it is. But decision trees with 70 nodes have a greater VC dimension. They can guarantee zero training error over a larger subset of instances. And so in a way, this axis is also the VC dimension axis. And what we were seeing is, as the VC dimension grows, if you hold constant the number of examples, which is what we did in this plot, don't change the number of training examples, but only change how complex a decision tree your learner can consider, then what you see is, well, if you have a small tree, then your training and your test error are very close to each other. They're within epsilon for some epsilon. But if you have a more complex, higher VC dimension tree, then those two things can deviate from one another a lot more. And as you grow the complexity of that hypothesis space further, then the overfitting problem can get worse and worse. Overfitting being the difference between these and if you think about it, these VC dimension results that we're talking about are giving us exactly this thing. In fact, this expression here is from the agnostic version of the VC bound formula that tells us how much can the true error and the training error, our test is really an estimate of the true error. And that's the training error. So this is literally telling us how far can the true error, that's this guy, this test error is an estimate of the true error. How far can it deviate from the training error as a function of the VC dimension, number of training examples, and our delta, the probability that we'll be able to achieve that. So this really is a quantitative characterization. This plus or minus quantity here is really an estimate of this distance. Right? So see why this is such a great thing to talk about before the midterm. It pulls it all together. We started out the class really worrying about overfitting. And now what we're saying is all this stuff that we've done for the last day and a half is really a way of trying to get quantitative about how bad that overfitting can be as a function of the number of training examples, the complexity of H. Those are the two things we really wish we could talk about. But in order to get our theoretical results, we also had to make this additional assumption of Well, it's in the PAC setting where examples are drawn according to the scheme. And we can't really guarantee that we'll get here. We can only say with probability 1 minus delta, you'll be able to have overfitting of at worst epsilon. But you see how it all comes together. So it's pretty cool. Okay, so any questions, comments, thoughts about this before we put this to rest for now? Yes?
I'm a little confused. When this expression really only says that it's greater than. It doesn't really tell you what error true H is. So when you say it's a quantitative expression of how overfit it is, that would be...
Yeah, good point. So you're saying the question was, isn't this a bound on the overfitting? And yes, it is. It doesn't say exactly what the overfitting will be. Because this is not an equal sign here. It just says the overfitting will be, with probability at least 1 minus delta, the overfitting will be no worse than this quantity. That's what it's precisely saying. Yes?
How useful are these forms in practice? Like if you are training some normal, do you make use of the forms or do you just
Right. The question is, how useful are these in practice? And the answer is, these bounds are pretty bad in practice in terms of telling you how many examples you should use. And their real use is to understand the kind of scaling properties. If I have twice as many variables, how much more data should I have if I want to have the same amount of overfitting? They're more reliable there. They're not very reliable in terms of giving number of examples. Okay, so let's say we've done enough for now. We may come back and after the midterm, I think we'll look at one of my other completely different favorite theory results on mistake bounds, but not today, because I do want to, oh, I see what I have to do. I do want to spend a few minutes talking about the midterm. Actually, quick announcement, just so everybody's clear on this. The midterm is open book, open notes, no computers. Sorry, no computers. And it covers everything that we've covered in the class. And will be reasonable. As reasonable as we can. Okay, so just to refresh you, here are some of the topics we've covered. And as you're preparing for the midterm, you might want to kind of make your own list. But when we made up our list, this is the kind of stuff we came up with. But I thought a little bit about what would be a good way to prepare for the midterm, and I have two things to say about that. I mean, you can prepare in your own way. What I always do when I take a midterm, honestly, is I try to pack everything that I know onto one piece of paper. And then maybe I'll bring some copies of slides with me too. But I know deep in my heart that I'm not going to have time to leaf through lots of slides when I'm under the pressure of answering a midterm in only 80-minute class period. So I try to summarize everything on one page. It works for me. But when I was thinking about what kind of summary, I think here's the kind of interesting way to go back through what we talked about in the class. You say, well, we talked about a bunch of different learning methods. And why? Why don't we just have one learning method? And what's the difference among these? And so I thought one way you could prepare for the midterm would be to try to characterize the different algorithms that we've talked about in terms of these kind of things. So, for example, we could think about naive Bayes and logistic regression, for example. And maybe we can just fill this out ourselves to get the feel for it. You may want to go through this for other algorithms too. But like, you know, the form of the learned model for both naive Bayes and for logistic regression, we want P of y given x, and we want P of y given x. But actually, and the inputs here for both of these, I guess, is a vector of inputs. So it's a feature vector with real or integer or discrete values. And I guess it's the same for logistic regression. And the output is discrete valued y. Same for logistic regression. Now, notice we've talked about other algorithms like linear regression, where the output was a real valued y instead of discrete valued y. So one of the reasons we ended up covering different algorithms is different types of inputs and outputs. But more interestingly, if you think about every one of these learning algorithms we've done, most of them you can think of them as the algorithm itself is a kind of optimization algorithm. Really, even naive Bayes and logistic regression, when we derived or justified the learning algorithm, we started with an objective. We said, well, we want the theta that, we want the parameters, we want to learn the parameters from the training data that maximizes the likelihood of the data, right? So for naive Bayes, really our objective is we wanted to maximize the likelihood of the data. We wanted to choose the parameters of the naive Bayes classifier that would maximize the likelihood of the data. Yes?
I'm sorry. I remember reading naive Bayes estimates probably x given y and probability of y.
That's true. So the point up here was, but naive Bayes doesn't really estimate this directly. It estimates it how? Right, it uses Bayes' rule. So we get that by having P of x given y and P of x. Did I say this right? That's a y. Right? So we end up estimating P of x given y and P of y. And of course we can get P of x from that, just by summing out, marginalizing out the y, summing out over the values of y. Okay, so that's right, good point. Whereas for logistic regression, we directly estimate this. In fact, we directly estimate this in the form of essentially, this kind of thing. So they're different in terms of their representations. Thank you. And in fact, they're different in terms of their objectives too, right? Because we use maximum likelihood, or we also agreed we could use map if we wanted. That gave us a slightly different thing. Remember we talked about beta priors and all that. But for logistic regression, what do we use? Conditional likelihood. So we used maximize conditional likelihood estimate. Okay. And then we can talk about, well, I won't go into the algorithm, the assumptions. What's the difference in the naive Bayes versus logistic regression assumptions? Right. So naive Bayes assumes conditional independence. Actually, both the representation assumes this and the learning learning algorithm assumes it. Whereas logistic regression, when we learn, learner makes no explicit conditional independence assumption. Right. Even though you'll recall that when we derived this form for logistic regression that we're using, we ourselves said, well, what if we made the same assumptions as naive Bayes? Then what form would P of yx take? And we agreed it would be that. So we said, well, let's use that. But then, of course, the training algorithm that you know about, gradient ascent, there's no conditional independence assumption there. So in the end, logistic regression can find boundaries that are different from what naive Bayes would find given the same training data because of that. Guarantees, decision boundaries, generative, discriminative. So I encourage you to kind of think about these kind of concepts because they're a way of bridging across algorithms and seeing kind of the space, the network of different algorithms that we've been looking at and how one is related to, similar to, but different from. What are those similarities? What are those differences? It's a great way to prepare for the midterm. Because, you know, you got to figure, what do we want to test? We want to test that you know the things we've covered in class, but even though it's kind of hard, what we'd really like to know is, do you understand the big picture? It's hard to make up questions about the big picture. We've been trying. But you know that's what we really want to know. Okay, so I would recommend going through this and just kind of filling out that kind of chart for your own. You could make a big chart of the different algorithms. What's the objective being optimized for each? What's the representation? What are the assumptions? Are there any guarantees? For decision trees, there's really no objective function explicitly. There's just this kind of heuristic, greedy, grow the tree thing happening that empirically happens to work pretty well, but it's a different thing. Okay, so the final thing I want to say, I also thought to myself, well, what are some of the fundamental ideas that I really hope everybody understands after the first half of the semester? And it's a simple list, but it's worth going through. So one is, learning really is an optimization problem, the way we're framing it in many cases. And that's why just about for every one of the learning algorithms we've talked about, we've begun by asking, well, if you get to pick the parameters, if you're the learner and you get to pick the parameters of the hypothesis, on what basis, what parameters would you prefer? How are you going to, what's your decision criterion? What's your objective function that you're really trying to optimize? And so that was one of the main ideas, I think, in the course. Second one is kind of a corollary of that is, well, therefore, many of these learning algorithms are really parameter estimation, optimization algorithms. For example, we talked about, we talked about these different objectives, and we also talked about to measure the accuracy, you'd have to look at the test data. But then, you know, what were the algorithms themselves? Well, the gradient descent is really just an optimization algorithm for any differentiable objective function. And so we kind of reduced the problem of learning a logistic function to the two subproblems of figuring out what's the objective we want to maximize the conditional likelihood, we said. And then, okay, what's an optimization algorithm that we can apply to that kind of problem? Gradient descent, we said. In other cases, like naive Bayes, we said, what do we want to maximize? Oh, the likelihood of the data given the parameters. And then we found, oh, we can derive exactly the expression for the maximum likelihood of these different parameters. There's things like, you know, the fraction of examples that turn out to have a value 1 over all the examples that had 1 or 0. But that was, again, an optimization algorithm that we derive from our objective of maximizing the likelihood. In fact, when we talked about linear regression, we did this interesting thing there, which I hope you didn't miss, of saying, well, let's minimize the sum of squared errors. Why on earth would you do that? Well, remember, we said because if we make this assumption about the probabilistic model, then we say we want to maximize the data likelihood, that turns out to be equivalent to minimizing the sum of squared errors. They're one and the same. Although just minimizing the sum of squared errors, well, we can turn that into an easy, there are a lot of problems. We can turn it into a matrix algebra problem, or we could turn it into a gradient descent problem very easily. And so it's kind of easier thing to think about than manipulating probabilities. And so in linear regression, we end up with this algorithm that never internally manipulates any probabilities. It's just minimizing sum of squared errors. But as observers, we can look at that algorithm and we can say, yep, it's getting the maximum likelihood estimates of those parameters, even though it doesn't know it. It thinks it's just minimizing the sum of squared errors. But we know they're equivalent. So that's the kind of game we've been playing. We've been playing this game. What's the objective we really want our learner to achieve? And now how can we implement an algorithm that will achieve that reasonably attractively? Okay. We talked about error and where it comes from. We talked about, remember one of the pictures that I carry around in my head is this one where I say, well, suppose we have a Gaussian naive Bayes classifier over one variable, and this is the learned p of x given y equals 1, and here's the one for y equals 0. And suppose we have enough training data to learn these perfectly. There's still some unavoidable error that we're going to get just because it's a non-deterministic thing. So that was one of the sources of the error. Another was bias. The difference between the true value of the parameter and the expected value of the parameter given our estimation algorithm. And we tried to develop unbiased estimators for almost all the algorithms that we talked about. And then the third was variance. That's the one that creeps in because we don't have enough training examples. And so if we draw 10 training examples at random and do that several times and train the algorithm differently each time on a different sample of 10 examples, we're going to get variance in the result of our learner. And that variance will reflect variance in that training sample. And that's another source of error. So it's good to think about those. And then today when we talked about PAC learning and how that quantifies the overfitting, again, that kind of ties it back together. And then finally, so these are all kind of interrelated themes. But to make learning really work requires adding usually assumptions. There is no free lunch. So we ended up making assumptions of different kinds for the different algorithms that we talked about. And it'd be good to go back through and review what were those assumptions and why are they helpful in some case. If we, so we make assumptions about the form, or sometimes we make assumptions about priors so that we could use map estimates instead of maximum likelihood estimates. And that leads to regularization, which can dampen out the effects of overfitting. Although it introduces some bias toward the priors. And we made other kinds of assumptions. We spent a lot of time on Bayes nets, mostly because we were so enamored of the idea of conditional independence assumptions that we wanted a more expressive way of stating them, and Bayes nets was just the thing. So as you're reviewing the material, I hope that you'll go through the details of what we did, but also try to put together your own big picture, because that's really, in the end, I think what's going to be valuable to you as you come out of the course. And the midterms are our first of 2 chances to do this kind of review. So come on time on Thursday. This is the only room available to us. Apologies to the student who sent me an email and say, can't we get a bigger room for the midterm? Sorry, they're booked. So come on time and we'll do it in 80 minutes on Thursday.
Guys, homework 3 is graded.
Yes, and here I'm setting the homework 2s out here.